So, have you ever actually stopped to think about how we describe motion and physical forces out there in the real world? I mean, think about it. If a massive passenger plane is flying through a heavy crosswind, or if gravity is pulling a heavy box down a steep ramp, simple, everyday numbers just aren't going to cut it. We need a way to mathematically describe not just the raw amount of force, but exactly where that force is pointing. And that simple, everyday necessity sets up the absolute need for what we call vectors.
Welcome to The Explainer. Today, we're incredibly excited to break down the absolute fundamentals of vector mechanics, going step by step. We're going to take this totally essential mathematical tool and completely demystify it for you. By the end of this, these concepts will absolutely change the way you look at the physical forces constantly at work all around you.
Okay, let's dive straight into this. Here is our structural roadmap for today. We'll start with scalars versus vectors, then dissect the anatomy of a vector. After that, we'll cover types and coordinates, run through some elementary vector math, and cap it all off with the scalar product.
All right, let's kick things off with Section 1, Scalars versus Vectors.
Now, what's really interesting about this is the massive divide in how we actually measure things in our universe. On one side of the coin, you've got scalar quantities. Think about basic things like volume, mass, temperature, or time. These are defined entirely by just a single number and a unit. If it's 20 degrees outside, you don't go asking, wait, 20 degrees in which direction, right? It just is. But on the flip side, we have vector quantities, things like displacement, velocity, weight, or even an electric field. Regular numbers just aren't enough for these. Velocity isn't just speed, it's speed traveling in a very specific direction. Without that directional arrow attached to it, your data is literally incomplete.
Moving right along to Section 2, the anatomy of a vector.
Okay, I want you to picture an arrow, just floating in space. To really understand vectors, we first have to build one in our minds. Every single vector out there carries 4 specific anatomical parts. First, there's the origin. This is the exact point of application where our arrow starts. Let's call it point A. Second is the support. Imagine an infinitely long, invisible straight line. We'll designate it as delta that acts like a track our arrow rests on. Third, we have the direction itself, which is the actual spatial orientation, pointing from point A toward point B. And finally, the modulus. Picture the arrow stretching out from its starting point to its absolute full length. That physical size represents the vector's magnitude, which always gives us a positive numerical value.
Which brings us nicely to Section 3, Types and Coordinates.
So, let's look at the different species of vectors based on how they anchored to their origin. First up, the free vector. And it's exactly what it sounds like. Its origin point is not fixed to any specific location whatsoever. A free vector can move anywhere it wants in space, completely untethered, just as long as its overall direction and its modulus, its length, stay exactly the same.
Now contrast that with the sliding vector. In this case, the origin still isn't pinned down to a single dot, but it is restricted. It can only slide back and forth along its fixed support. Remember that infinite straight line track we visualized earlier? It's stuck on that track, but it can freely slide up and down it.
And then we have linked vectors. Unlike the free or sliding ones, this guy is entirely locked down. Its origin point is permanently fixed to one specific, totally immovable starting location in space. No floating, no sliding.
And that brings us to a really cool, very special category, the unit vector. What is it? It's simply a vector whose modulus, again its length, is exactly equal to 1. So the crucial point here is that a unit vector is essentially the absolute purest mathematical measurement of direction alone. By stripping the magnitude all the way down to a baseline of 1, we isolate just the directional orientation. And trust me, that is incredibly useful for complex math.
And this brilliantly illustrates exactly how we take those vectors and map them into three-dimensional space. We use a Cartesian coordinate system marked with a base frame, O, and unit vectors I, J, and K. But how do we figure out the orientation of these 3 axes relative to each other? Physicists use something called the right-hand rule. You can literally do this right now. If you align your thumb, index, and middle finger at right angles, you are physically modeling the positive directional flow of 3D space. Once that's set, any vector at all can be perfectly defined by its specific x, y, and z components.
Let's step into the physics playground, shall we? Section 4, Elementary Vector Math. Vector addition is just wonderfully visual.
You see, if you want to add vector A to vector B, you can't just mash their lengths together like normal numbers. You have to account for their different directions. Visually, if you draw vector A and vector B starting from the exact same origin point, you can use their lines to sketch out a complete parallelogram. Then, you just draw a diagonal line cutting straight through the middle of it, from the origin to the opposite corner. Boom! That brand new path is vector C.
Now, there's another way to look at this, a beautifully simple physical logic for adding vectors head to tail, known as the Charles relationship. Imagine you've got 3 points, A, B, and C. If you have a vector taking you from point A to point B, and then another vector taking you from point B to point C, well, adding them together gives you a new vector that goes straight from point A to point C. The final displacement is exactly the same no matter the path you took to get there.
Let's move on and see how this builds into subtraction. Vector subtraction is an anti-commutative operation. Fancy word, but practically, taking vector A minus vector B is really just taking vector A and adding a negative vector B to it. And what exactly is a negative vector B? It is literally just an arrow with the exact same length pointing in the exact opposite direction. You just flip it around.
We can also combine vectors with regular numbers, which is a process we call scalar multiplication. If you multiply a vector by a normal scalar number, let's call it alpha, you're basically just scaling the length of that vector up or down. If alpha is a positive number, the arrow gets longer or shorter but keeps pointing the exact same way. But if that scalar number happens to be negative, the arrow violently flips around and points in the completely opposite direction.
Which finally brings us to section 5, the scalar product.
Okay, here we have the scalar product, which you might sometimes hear called the dot product. Imagine 2 vectors colliding, both starting from the exact same point. There's naturally an angle between them, right? We'll call that angle theta. To find the scalar product, you just multiply the length of vector A by the length of vector B, and then multiply that by the cosine of the angle theta. Now here's the kicker. The output isn't a new arrow. It's a single normal scalar number. That angle theta fundamentally determines everything here. It mathematically tells us exactly how much of vector A is acting in the exact same direction as vector B.
So what does this all mean for us? We've covered the origins, the spatial mapping, the whole underlying math of vectors. But remember, these aren't just abstract concepts drawn on a chalkboard. Vector mechanics mathematically dictate absolutely everything in our physical world. From navigating a giant airplane through a vicious storm to mapping the invisible electric fields powering the very device you're watching this on. So I leave you with this. What invisible arrows are acting on your body right at this very second? Next time you feel the wind push against you or feel the heavy pull of gravity, try to actually visualize the modulus and direction of that vector in your mind. Thanks so much for joining me on this explainer, and definitely keep questioning the physical forces around you.